I think we should continue. So, where did we? Okay. So what do you see from this picture? You see that the spacing between these lambda levels is not constant. So and for the low energy is bigger. As I said, the reason is that these particles always move with the same velocity. So the Lorentz force, which is actually the electron charge times the velocity times the magnetic field, is always the same. But if you see this, if you remember those cones, that in momentum space, they have to make, if you go towards the zero energy, they have to make smaller and smaller loops in momentum space. So that means since the Lorentz force is the same, dp dt, they have to make smaller. In order to make a loop, you need less momentum. They're going to move. The frequency will increase and actually becomes infinite. If you quantize it, then you get these quantized levels, Landau levels, where you clearly see that the spacing is not constant. Here it's the biggest spacing. You also see that now we get a Landau level at 0. And as I said, this you can understand as the addition of this extra phase factor of pi due to this Berry phase behavior of this pseudo-spin variable. So if you look at it again, now if this is in the center, now again if you go towards the edge, you see that the zero Landau level actually has two. Well, it's made up of two Landau levels because one of them goes up. This is the electron part, and the other one goes down. That is the whole part. So, but you see also something like this, and I think this is quite funny. You see that also the higher Landau levels, they split. And does anybody has an idea what is going on? I should mention the degeneracy. So the degeneracy is 4 here, because we have two spins, one up, one down, right? That is always so. I mean, that's just a factor of 2. And we have two valleys, k and k prime. So the degeneracy is 4. But we nevertheless see that if we go towards the edge, this Landau level is going to split. So has anybody an idea why this would be? So somehow these electrons are feeling the properties of the edge. And I cannot say too much about it, but just show you let me show you the edge structure if I can. Oh, I need to go. I'll just draw it here. Of course, this is one typical edge structure which is called armchair, because you have a nice chair here and you have a nice chair here. And the other one obviously would be, if you nicely draw it, you have the hexagons here. You get an edge structure which is zigzag. And since, of course, when these electrons are pushed towards the edge, and when they're going to perform the skipping orbits, they're also going to feel the boundary condition which is put on by the edge. And in this case, let me just, the boundary condition is such that there will be a difference between the electrons in the k and the k prime valleys. So you could say, well, that's interesting physics. You can still use the edges. In most cases, however, it's a nuisance because you cannot control the edges. How do you, if you really want to make a nice piece of graphene and we want to be sure it's zigzag edge or it is armchair edge, that's pretty difficult. So you have no control, or you say very little control about this splitting. On the other hand, it's usually much smaller than this splitting, so you do not really care about it. Can you now say something, if you look at it, about this behavior of this quantum Hall effect in single layer? Well, if your Fermi energy goes from here to here, you exceed you basically cross one Landau levels. It's 4 times degenerous, so it gives 4 e squared over h, which is the standard step. But this guy basically is already split up here. So here the degeneracy is only 2. Yeah, so you can also understand this anomalous behavior of the quantum Hall effect in single layer graphene with this picture. So now there was a clever question. Somebody, I think it was you there, asked, hey, wait a minute, but you should also say something about what happens in double layer. Yeah, because maybe the same thing happens in a double layer. So let's now turn to a double layer. Okay, no, before we turn to a double layer, let's just mention this one. So this is the Landau level sequence in single layer graphene. This is the zero energy. We had a very big, relatively big energy spacing between the first, well, the zero Landau level and the first Landau level. So if you express this in terms of temperature or in Kelvin, you get something like this. And this is interesting because it tells you that if you have a field of only 1 Tesla, which is not so big, then this typical spacing is already corresponds to a temperature of 420 Kelvin, which means that you can actually observe the quantum Hall effect even at room temperature. This was shown in Nijmegen, I believe. Well, they used a much bigger field, about 30 Tesla. This is at room temperature, and you see also this is again the whole resistance as a function of the gate voltage. And you see the clear formation of the plateaus. It's of course not very accurate yet, but they are at the proper values where they should be, already at room temperature. And the reason is because of this relatively big Landau level spacing, because of this very, very fast cyclotron orbit motion. So you could say it may be useful because the quantum Hall effect is used as the standard for resistance. If you now can do, instead of having to cool down your sample in a cryostat and apply a magnetic field, if you could do that at room temperature, that might be useful. Well, certainly this is not yet useful because it's not yet the plateaus. This is certainly not an accuracy of 10 to the 8th or 10 to the, well, 10 to the minus 8 or 10 to the minus 9, which you need. But who knows what might come out of that.
Question?
Yeah?
Can you go back one slide? Oh, one more. That one, you said the first energy level, it's split into degeneracy?
This one.
Yeah.
Yeah.
No, the next one.
This one.
Yeah. So there's actually a minimum on the bottom of the 2 degeneracies?
Yeah.
Can you say something about that?
No.
Okay.
I had a look at this calculation. It's 3 pages long. And, well, I had another look at it. And then I said, well, let's not do it.
Okay.
Yeah? So this is complicated. Okay, I can say a little bit about that because if you have in the bulk of your graphene, so maybe that's, okay, then electrons can sit in K and K prime valleys. To go from a K to a K prime valley, you really have to invest a lot of momentum, yeah? Because you have to, and that is usually not so easy. Yeah, so you could say, well, most of the action is happening with electrons which stay close to the K value or stay close to the K prime value. And you can actually use this. I mean, it's sometimes called valleytronics. So the main lesson is that in the bulk, these K and these K prime values do not mix. However, if you have one specific edge, which is the armchair edge, you can really, you can see what is happening. There is an electron coming, which is described by some wave function, and it's basically reflected from this edge. And if you now want to impose a proper boundary condition, then you find that you have to use both valleys. So actually the scattering from the edges mixes the valleys. And this is a reason why this splits up. And this apparently works in such a way that the energy can even go down. Yeah?
Yeah, but wouldn't it mean that it's a more bound state where it's a lower energy? More stable state?
I would not
Because it's
use.
a low field signal.
I would not use that. Okay. In principle, it would be possible if you tune your Fermi energy to sit somewhere here where you have this state occupied and not this one, right? So you could use it, but that is very, very complicated, I think. And you have to realize that this is obtained from a calculation. I think this is the simple calculation where you only include hopping between neighbors, between the A sites and the B sites. Well, it's not yet clear if you really need to include also the hopping between the A sites and the A sites. So you could say some next nearest neighbor. But if you would include that, then already this kind of subtleties will already change. Yeah, but this is not subtle. This is there. This is rigid. Yeah, this. You cannot avoid this. This one is a bit more subtle. Bilayer graphene, that was the question. So if I now say this anomalous quantum Hall effect is proof of single layer, then at least I have to show that bilayer graphene behaves differently. So this is bilayer graphene. What you see is that you basically have your hexagonal lattice and you have shifted, let me see if this is correct, yeah. You have basically shifted the layer on top by basically half a lattice spacing. Doesn't matter too much, because, but you can realize what you have to do now. So if you now really want to look at the electronic state again, well, we have used this hopping between the A sides and the B sides to calculate the states of single layer graphene. Now we have to use, of course, the coupling. We have to include the coupling between the different layers. And you can, of course, do that by, well, in first order, is by introducing some coupling element, which is the gamma 1, between these two atoms which happen to be on top of each other. Yeah? And of course, you can also take a coupling between this one, and it gets more and more complicated. But let's only include this one. Then you get a Hamiltonian, which is a little bit similar to what we have seen before, but now it looks like this. So now it does not have, well, first of all, it already has a mass. That's already the difference. The single layer basically did not have a mass. This one has a mass. And you see that now it still has only elements on the diagonal, but now you see that there is a square here. Details are not so important. What is important, what finally comes out of it. So now, in single layer graphene, we basically had this nice diagonal cone shape dispersion. And basically the energy depended linearly on the momentum, which basically said, well, which means that we had this massless electrons. Here we get something which still has a nice curvature, which then corresponds with a certain mass. This is the sequence of Landau levels. Again, this is not it's not an easy calculation, but it's very different from graphene, from single layer graphene. I can just show it here. Just look at this one. This was the normal situation, where I just have this fixed sequence of Landau levels which are equally spaced and have a spacing of h bar omega c. And here, this was the situation for single layer graphene. Here we had this special zero energy Landau level, then we have the next one, and then with the biggest energy spacing and become smaller and smaller, and of course we can go also in the whole regime. This is the case for bilayer graphene. There is still this behavior that the spacing is not fully constant, but what is special is that the degeneracy of the Landau level at zero energy becomes twice as much. I don't have a good argument for that. It is also related to some kind of Berry phase, but it's important to realize that now if you change your Fermi energy from here to here, then of course the occupation of this Landau level goes from 0 to 1, but you changed twice the amount of states as if you would go here. Because so that basically means that again, and this is the bilayer case, if you now look at the bilayer case, you have a jump. Well, this is 0, and this is the first plateau. Now you see that you do have a regular that all the steps basically are the same. So whereas in single layer graphene we had the first step was only half of the rest of the steps, here all the steps are the same. So this is how you can recognize. It's a bit technical, but certainly how you can distinguish a double layer from a bilayer. In principle, you can go on to 3 layers, etc., but then it becomes more and more messier. So this is the answer to the question. If it would be bilayer, then it would behave like this. What can you do with bilayers? There's a very important thing which you can do, which single layers do not have. There's no gap in single layer. So you can not switch off the conductance of a field effect transistor. Well, remember this typically Dirac shape. At the neutrality point, the resistance is the highest, but it's still a few kilo ohm. I mean, it should be mega ohms or whatever if you really want to make a decent transistor. We can switch between on and off. So you have to think about the solution, and what you can do in bilayer is the following, and I will try to illustrate that. This is the 2 layers, the A and the B layer. Now I'm going to make a gate on top, which you call gate 1, and I'm going to make a gate on the bottom, gate 2, and I'm going to apply a positive voltage to this one and a negative voltage to that one. So if this would be a single layer, there would be no effect, because this positive gate voltage wants to attract electrons, the negative gate voltage wants to attract holes. If these gate voltages are the same, there's no net effect. If it is a bilayer, there is also no net effect on the density, because it's still zero, but there is of course an electric field. This makes an electric field, like this. So the potential of this layer will be a little bit higher than the potential of that layer. So the energy levels, if this would be isolated levels, or let's say if it would be two independent layers of graphene, the energy level of this one, well, this is, I always have to be careful with the potential, would shift relative to that one. Yeah? But now it's bilayer, where we already know that we have to include the coupling between these layers. So let's see what happens. I'm just going to show you this Hamiltonian in the matrix form. Why? Because we already saw that we already derived this. Basically, this is from the single graphene behavior. This describes the, you could say the rows and the columns. This one basically describes the wave, the wave function on the A side in the first layer. This is the wave function on the B side in the first layer. The A atoms in the second layer, and this is the B atoms in the second layer. Well, obviously you recognize that this mechanism, you can include that by adding a negative potential to these elements and a positive potential to these elements. And now you have to run the machinery, you have to diagonalize it, etc., and calculate the energy levels, and this is what you get. This was the case for bilayer graphene without any voltage, so these two layers are basically equivalent, and this is a voltage applied, and now you see, nice thing what happens is you change the band structure and now you have a gap. Yeah? So there is a range of energies where there are no states. So in principle, if you have, if you can also at the same time shift your Fermi energy, for instance, how could you do this? Suppose you apply, let's say, plus 10 volt here. Let's assume 10 volt, and this is minus 10 volt. Yeah. So that would give you this kind of band structure, like this. And now let's say you make this plus 15 volt, and this would be minus 5 volt. So the difference in the gate voltage remains the same. So your electric field remains the same. So your band, your splitting remains the same, but the only thing you have done now is you have changed the average gate voltage. So in one case you have attracted more electrons, you have attracted more holes. So basically you have shifted, you can shift the Fermi energy. And now you see what happens. If your Fermi energy sits here, you have states. Here you are in the gap, there are no states, so you have a high resistance, and then again you go into the electron state. So now in principle, by this trick you could make a, artificial semiconductor. Is this very practical? Answer is really not really, because this really depends also on the fact that you have, first of all, you have to make a relatively big electric field, because these layers are very close together. Yeah, so this, even if you have a big electric field, this potential changes only a little bit relative to that one. So it's not so practical, and also you have to have material which is really, really high quality. Otherwise, well, there are all kinds of imperfections which messes up this behavior. But in principle, this is what you could do. Okay, let me say a bit more about graphene in general. So this is what I basically discussed. There is a nice analogy with high energy physics. There is a Dirac-like equation for massless particles. I have not basically explained, okay, I think I've explained the Dirac equation, which you can actually describe for the generation of electrons and holes from radiation. There is an interesting phenomenon which is called Klein tunneling, which is, which also can be modeled with graphene. I'm not going to say much about that one. We have clearly already two-dimensional physics, quantum Hall effect. We can go to one-dimensional systems. We can make ribbons. We can make quantum dots. And people are doing that. We are also looking into that by really etching out small regions of graphene. We can also use some kind of self-assembly. That's also very nice. So you can basically make molecules which basically consist of a lot of hexagons in a nice regular way. If you can really increase that, you can really make artificial graphene. So that is, I think, a very interesting direction. Technological application, let me just mention gas sensors. So the nice thing about graphene is that all the electrons are at the surface. You could say, well, so what? In metals, they're also at the surface. But if you put something on metals, you only change the conductivity at the surface. And there are lots and lots of layers below. So the relative effect will be extremely small. So whatever you put on the surface of a metal is not going to change the properties too much. In graphene, obviously, it will. Because all the electrons in the graphene see what is on the surface. So you can use it to detect gas molecules or gas atoms even, and with a very high sensitivity. You can actually even measure one. If you make your device small enough, it was shown that you can really see steps in the resistance, and each of these steps should correspond basically by having just one gas atom or one gas molecule absorbed somewhere to your graphene. So that's a very sensitive way to do that. I have basically already said that you could think about making alternatives for silicon technology by imitating by making artificial semiconductors using bilayer graphene. That is clearly not, still in its infancy, because people are trying to do that, and you really have to explore this. So of course I'm not going to believe that graphene will replace silicon, but certainly in the area of sensors, in dedicated devices, clearly graphene is already making an impact. Graphene preparation, the Scotch tape method I've shown, not very useful for applications obviously, because it has a low cost part, which is the Scotch tape method, but it also has a high cost part. You really have to find where the graphene sits. There is the chemical CVD tricks. You can prepare graphene on metals. There are other techniques, and tomorrow I think there will also be demonstration of graphene. We will also show some graphene which is also made in a different way. There are also some techniques for preparing graphene layers by picking it up from the surface of a solution. I'm not going to say too much there. Graphene spintronics, I probably will not have too much time to discuss about that, but that is clearly also in a very relevant direction. Suspended graphene. So I said, hey, that's not so nice. So the graphene in principle has nice properties, but it has to sit on a substrate, and the substrate is silicon oxide, and that is not a nice smooth material. So let's get rid of the substrate. So how you do that? Very easy. Okay, we had silicon oxide, graphene. Yeah, remember this picture of this field effect resistor. We had contacts, gold. Well, now we make a device like that, and we put it in HF. HF is a very nasty acid which eats up quite a lot of things, including also people, if you're not careful, bones, for instance. But it eats up the silicon oxide, but it doesn't eat up the gold. So imagine you have your gold here, starts to eat up the silicon oxide, and it stops at the silicon. So what you can do is, if this would be a silicon oxide, you can actually make now a region where this graphene, in principle, where this graphene would be suspended. Of course, you have to be careful, because if you would have this in a solution and you take it out and you let it dry, of course there will also be always the interface between the, well, this is going to dry, so this will be there will be still some liquid here and no liquid there, and which will basically move in certain direction because it dries, and there will be some surface tension which can actually destroy your graphene. So you have to dry this in a careful way, but then indeed you can make suspended graphene. Now you're not there yet because there is still all kind of junk on the substrate. So what you do is you pass a very high current between there and there. So this is another property of the graphene. It's a very good electrical conductor. It's also very rigid. So you can achieve very, very high temperatures without the graphene disintegrating. But what happens with all the other junk? It disappears. Well, it evaporates or whatever. So this is called current annealing. So in that way you can really make a graphene layer which is almost ideal. It is very nice. This is a picture of such a layer. This is done with a transmission electron microscope, which has a very, very high resolution. So this is single, this is already a bilayer. I had a movie, but it doesn't work. But what you see is, of course, you can recognize, and this is nice, the armchair edges. And here there are the zigzag edges, but you see there is something attached. It looks like there is still something attached to it. So it's not clear what it is. It could be maybe hydrogen or something like that. But the trick is that what is done here is that a high energy electron beam is focused on the graphene, and there is a detector underneath, and of course the beam is scanned, and that of course makes finally a picture like this. But at the same time you can actually see that the hole which is formed here grows. So you could say actually some of these atoms are basically bombarded away when time progresses. So you can make controlled, if you like, you can make controlled very small holes in a graphene membrane. So what can you do with it? Well, people are actually looking into that. So if you have a small hole and you have a DNA string, and you have a trick to basically pull it through this hole, and in the meantime you can measure the resistance, the electrical resistance between the top and the bottom. And you might imagine that if a unit of the DNA, which is a little bit bigger, fills the hole, that the conductance drops. It's more difficult for ions to go through. And if then a smaller unit follows it, the conductance goes up again. And then, of course, you can make a nice DNA. You can sequence with this technique. So this is a little bit of future activities, but still it shows what you can do with this kind of graphene-based membranes.
Question.
Yeah.
If you would perform the electron diffraction, what kind of pattern you can obtain in the area of single layer and double layer?
Yeah, for a single, I would say it's basically the same principle. Well, it would be the same as the as a hexagonal pattern, yeah. And for the double layer, you have to be a bit careful. Applications. This is graphene, probably not a single layer, I have to say, on a flexible substrate. What is the problem with optoelectronics? So the problem is that you have to get the light out on some direction. So this is a light emitting diode. This is actually, well, apparently this is based on organic materials. You have the cathode, you have an anode. You have to apply, obviously, a voltage between them. You have to supply the current. But the problem is that one of these electrodes has to be transparent for light, because the light has to go in. And the material which is used is indium tin oxide, which is a rather, I mean, it's certainly not an easy material to handle. You would like to replace it. And one way to replace it is, for instance, to replace it by graphene. Because this is very, very thin. It's a relatively good conductor. As we've shown, and it has a very nice aspect, is that it has something which is a universal light absorption. And universal means that the absorption of light in a specific regime, so it's not UV and it's not infrared, but somewhere in the light regime, and the absorption is given by pi, well, which is well defined, times alpha, and alpha is the fine structure constant. It's so typically 1 over 137. So basically one layer of graphene absorbs about 2.2% of the light. And 2 layers you can basically add the absorption. And of course that is not so much. So if you make a single, one of these electrodes out of graphene, you only lose something like 2.2% of your light, which is not so much. By the way, this is also related to the Scotch tape method. The fact that we can really distinguish single layer graphene from 2 layers, from 3 layers, is a bit related to the fact that this absorption nicely increases with the number of layers. This is a nice one. I want to show this because it's a funny trick. So let me just make a... This is a material which has an index of refraction N1, and this is N2. So now we have a light coming with a certain angle, and now it is, this is called theta 1, and this is called theta 2, right? And now we have a law which says that the sine of theta 1 divided by the sine of theta 2 is N2 over N1. This is Snell's law, after a Dutch scientist, Snellius, yeah, which is basically the fundamental law for diffraction. But what you see is the only thing you can do, if you enter with an angle like this, you end up with an angle like this. Yeah? Yeah? So why is that? Because usually this index of refraction is positive. Yeah? However, you can in principle also make materials which have a negative index of refraction for light, which is a tricky business. I will show you that you can also do this with electrons using graphene. So what do? This is my graphene layer, and now I make it into two regions. I have one region where I have a gate, which can be on top of on the bottom, it doesn't matter too much. I apply a positive voltage. This is my gate, I apply a negative voltage. So remember, positive voltage is going to attract electrons. So what I also have is the system. This is my energy diagram. This is the Fermi energy. So you should realize, of course, that the system is in equilibrium. So the Fermi energy is like a C, the Fermi C is always the same. Yeah? But I have attracted electrons here. That basically means that I have pulled down all the energy levels. So here this would be my zero energy, and here of course I would have my cone for, in this case, the electron states. So here I have the same thing, but now the opposite way. I have basically, this would be now my Fermi energy, this is my zero energy. Now I am in the regime of the hole, so this is now my cone. Yeah? And now the trick is the following. I have a source, this is a source of electrons, and I have a probe. And I want to know, can I now make an image of this source here? Yeah? So as simply, well, can I make basically a model of a lens? Yeah, because that is what a lens does. If I put a lens here, then I will start, my rays will start from the source in this direction, and that has to be, the direction has to be changed and focused in the direction of my focal point here, and here the same thing, etc. So it would be a lens. Can I make a lens with it? And the trick is, yes, you can do that, because let's look at it. So now we have to be, always have to be a bit careful. So let's look at electrons which have a velocity in this direction. So that would be basically electrons sitting here. If you sit on this cone, this electron has only has no velocity in the y direction. It has a velocity in the x direction. Where can that go? Well, it has to conserve the energy, because the energy will remain the same. So it has to end up here. Yeah? Because this is the slope of the cone. Yeah? So here, again, yeah, this is the slope of the cone. It has to be the same. So it ends up here. Yeah? But you see that the momentum has changed. Yeah? Because clearly this was zero momentum. This had here at the positive momentum. Now it sits on the other side. The momentum has changed. Well, is that now clear why it did so well? Yeah, because there is a difference in potential. There is an electric field here. What you can now show, let me now show, that as a matter of fact, what happens is the velocity. So by the fact that you have to, well, basically you go from an electron cone to a hole cone, and you have to change. The velocities will remain the same, but the momentum has changed. You can actually show that you get a pattern like this. So that electrons which start out in this, in this region, they go like this. Then at the interface, the motion is changed like this, and they're basically focused here. And the same holds for electrons here, etc. Of course, I have to say that this has to be perfectly symmetric, because the plus, the gate voltage which you apply here, and they have to be exactly opposite, so that I get a nicely symmetric picture. Then you can actually get this. And of course, that's very nice because you have some artificial lens. You don't have to do anything special. No complicated geometries, just a transition between a p-doped and an n-doped region. Is there a drawback? The answer is yes, because this is ray. Well, you could say these are rays. It's like geometrical optics, and of course you know that there is also a thing like diffraction, if you really take into account that, well, light actually is waves. Also these electrons, of course, they have a certain wave aspect. So it turns out that you cannot truly focus all these, even though you start with a point, you cannot truly focus it in a point. You always get something which has a finite size, but it's not necessarily a problem. What is a problem is, of course, that you really have your graphene has to be in extremely high quality, because suppose your electron is scattered here, then it will go a different direction, and clearly it will never end up nicely in a point like this. This is called a Veselaho lens. There is a Russian scientist who basically came up with this idea. Again, it looks like you have made a material which has a negative index of refraction. I am going to skip this part, because this is what basically our contribution was to graphene. In view of the time, let me just skip it. So I want to go to the last part. And the last part is, can we have graphene at home? This is my daughter, my youngest daughter. And I have put her here to give a little bit of impression of the size. This is an electrostatic loudspeaker. So when I have time, which is not too much at the moment, I have some projects at home. This electrostatic loudspeaker, it is very simple. It is basically a frame of wood. These are PVC tubes, just from electricity tubes. And here you see these nice colors, they're just electricity wires. So this like this. There's another stator like this, and the idea is that you apply your sound signal, you apply this between the stators. And the idea is now that in between you have a thin membrane, and you put it at a certain voltage, high voltage. Why? Because you want to have a big charge to sit on the membrane. That's the only role of the membrane. Here you have your sound signal, so the electric field of the sound signal pushes this membrane back and forth. So this is how it works. The nice thing, of course, is that it can be relatively light compared to regular loudspeakers where you really have to move much more mass. Here this membrane can in principle be very, very light, so you can have high quality sound reproduction. Well, I was just interested in the principle, and I didn't want to spend too much money. So that is why wood, etc. And this membrane, what I used for the membrane was kitchen foil, like this. Yeah? You can really stretch it. Well, of course, it will tear after a while, but you can really stretch it, as you know. But now comes the problem. You have to make it conducting, because it doesn't have to conduct much, but just enough to keep that you can have a charge on it. There are several ways. One is soap, but that's very, very tricky. And the other one you can already guess. That is graphite. So the idea is you take this. You take the graphite, you take some cotton wool. I'm not going to illustrate it here, but you can imagine you put the graphite on and you smear it out. And you smear it out quite a lot, because otherwise you get all these graphite particles. You don't want it. You really want to have a smooth layer. And now it says, this is from a book. Well, it's in Dutch, but I will translate it. From a do-it-yourself electrostatic loudspeaker book. It says what you should do is you should rub out this graphite, and typical resistance value should be of the order of 10 kilo ohm. I had not seen this, by the way, because then it would already have rung a bell, because you remember this is 10 kilo ohm, that is almost close to this unit of resistance, of unit of conductance. Fine, well, I can tell you what I measured at home, 5 kilo ohm, which is almost the same as people measure in these in these graphene field effect transistors, right? So what is now happening? Again, I cannot prove it, but the idea is, again, it's basically analog of the Scotch tape method, right? Of course, this graphite is very messy. So you rub it out, and there will be maybe some relatively big flake sitting there. But then, each time you go with your cotton wool, you take off more and more layers. And of course, finally, of course, you get a conducting path. First of all, you're below the percolation threshold, very high resistance. And then you put on more, you get a conducting path. And then when you get this conducting path, your resistance is 5 kilo ohm. Certainly not uniform layer, absolutely not. But it seems to indicate that the critical conduction path is actually determined by a single layer. Because if I would have 10 layers, I would not measure 5 kilo ohm, I would have measured 500 ohm, 10 times as small. So then I came up with the idea how you make your own graphene transistor. So this is the foil. So first you make the gate. Basically you cover one side with graphite, and then it doesn't matter if it's thin, just has to be metallic. That's going to be your gate electrode, right? Doesn't matter too much. Then you turn it around. Yeah? Then you really cover it with graphite and you rub it out, because that has to be your single graphene layer. Yeah? Measure the resistance. Then you apply a DC voltage between your layers. You have made, and then, so this is your gate, and then you measure the resistance. I have not tried, I've tried it at home, but the problem is that if you cover one layer with graphite, one side, and the other side, there is a relatively big probability for short circuiting. If you do it carefully, I'm sure that you must be able to do it. So that you do not have a short circuit, right? There is a problem that this foil is a micrometer thick. So you need kilovolts probably to apply for your gate voltage. So if you do it, please be careful. I was not able to do that yet. But you can try and convince yourself that if you measure the resistance of this one, indeed you get something like 6 kilo ohm. So I'm not kidding. Okay, I think if you have the time, I would, and allowing for some more questions, I'd like to stop here. I've given you a glance of what can be done with graphene. I actually wanted to make a list of all the topics which I did not discuss, but I said, well, let's not do it because that will take several slides. Let's not do it. If you want to get more information, since we are now at FOM, I like to refer you to this website. Well, very easy to remember. Which actually is the website of the FOM program on graphene-based electronics, which involves groups from Delft University, Leiden University, Groningen University, and Nijmegen University. And here you see some input of the various groups into that program. You can look further there and get some more information. Okay, I like to stop here. Thank you for your attention. Are there questions?
You mentioned the technical application in terms of gas sensor. How reversible the membrane would be once the gas species is attracted to the surface?
Okay, let me go back. Let me see
how you can retract it.
It is basically physisorption, right? So it's just sticking to the. You can remember. Okay. So there are two effects which can happen if you put an atom or molecule on top of your graphene. One of them is that the charge transfer. There could be some charge transfer between the molecules, so it's actually doping. Mm-hmm. So obviously that will change your resistance. The second one is that it induces scattering. Yeah, so scattering, of course, always reduces the resistance, and if you include doping, well, it depends where you are. If this is your Dirac point, neutrality point, if you sit here, then clearly, okay, if the doping goes this way, then you increase your, you reduce the resistance. If you go this way, so the two effects which you could also use to distinguish the type of molecules. But basically, this is used for this is physisorption, which you can reverse. You can also functionalize the graphene, but that's the next step further. That indeed you only make it these functional groups connect with the molecules you want to detect. That is already a very active area in the area of nanotubes. For sure, it will also have some consequences here, but it's more complicated. This gas, okay, maybe I should show. Okay, I think maybe let me get. You already see these effects. For instance, if you measure this curve at room temperature, in atmosphere, you do not get a nice curve. what you get is hysteresis. Basically what you get is, if you go this way, then you get a peak here. If you go this way, then you get a peak there. Why is there? There is basically charge on your graphene, which can come there and go away. So this is always measured in vacuum, but it shows the sensitivity of your graphene to whatever is on it.
So I have a question for the application. What kind of length?
Sorry?
No, continue. Or even electrical length. Yeah. In one slide, it continues like a length. It focus the.
The lens. The lens.
Yes,
oh, okay. Let me go.
How could you control theta C and theta V, and what does that mean?
Okay. So, you mean
another slide for continue?
If you want to change the strength of the lens, right?
Yes, because another slide you have theta C and theta V. How could you control that?
Yeah. So if you want to control the strength of the lens, it's pretty clear what you can do. I mean, you increase your gate voltage here, right? But the problem is I don't have the drawing. You're always stuck to the principle that this distance has to be the same as this distance. It's not like a real lens where you're different. If you approach the lens, then this focal point just changes. Yes. That doesn't work, because if you do that, then if you would approach in this situation, you would put your point here. Then there will still be some focusing, but they will not all end up in the same point. So that you really have to have a symmetry plus between the two sides. But then you can change the strength of your lens by changing these two gate voltages. So I don't know if this is a very useful thing, but certainly it's a nice example of the strange behavior of electrons in graphene. Yeah?
Is this something that is actually being measured then?
I don't think so, to be honest. No, what people have been focusing a lot on is this interface, because you have the transition from P to N region, and but this in this shape, I don't think it has been measured, because it's very complicated. You really have to have your electron scattering mean free path has to be bigger than this spacing, because if the electron scatters here, it doesn't work anymore, and that is very difficult to do. Well, if you have suspended graphene, you could do it. But then you have to make it suspended, you have to have two tips, it's very complicated. It's a complicated experiment, so I don't think it has been done already.
What is in your view the most important challenge for this field?
I did. Well, obviously, I thought about this question, and to be honest, okay, I could say, well, that you control this graphene technology to such an extent that you can really, in a controlled way, make devices which have a well-defined band structure, like this example with bilayer graphene. But then, basically, I'm already assuming that this is a useful way to go, and I'm not convinced about that. So I don't think your question has a single answer. And what we do know is that the amount of activities in this area is so big. There's even in a graphene supermarket. You can look it up. You can buy all kind of graphene. There is Graphene Times, where all the news on the graphene is there. So that basically every relevant aspect is already being looked at. What is of course very crucial, and I think that is certainly an element which is important, and that this is not a practical way to make graphene devices. It's very nice to explore the fundamental properties, but it's not a. What you like to have is a well-defined way to make graphene layers on a substrate. Yeah? For instance, by these techniques which I've shown. There is one group, the group of Walter Heer, which I should mention, who actually was already doing that for several years, with trying to make graphene layers on silicon carbide. And what they did is they took silicon carbide, they heated it, so that the silicon disappears from the surface, and then you're left with several layers. And the problem was there that they could not show that it was single layer graphene. And then you needed the Scotch tape method. So I would say certainly there has to be more developments in that area. So you can really make relatively large size graphene layers, high quality graphene layers, because there is no fundamental reason why they cannot be done. So I think that certainly would be one of the challenges.
Is it really the strongest material?
It depends on what you call strongest, but I mean if you have per thickness, it depends on what it's usually defined as the percentage by which you can stretch it. Because this can be stretched by 10% or something. And there is, I think, I mean, I'm not an expert in mechanical properties, but there is one important reason for that, because there are very little defects. Because I showed you this transmission electron microscope. Well, this is only a small area, but people have actually been looking for defects, and they could not find any defects. So there is no, if you start to tear it, of course it starts to break somewhere. But if there are no defects, it cannot really start somewhere. So this is one reason. I think this is, it can be strained by 10%, and which is more than any other material.
And the spider net is more flexible?
Sorry?
For example, spider net.
Yeah, okay.
Which is said to be...
okay, it can be strained, and the force which it can then withstand, normalized to the thickness, is the biggest one as you can have for all materials. Yeah. So I think that is the... Yeah?
So you've shown us basically the integer conformal effect. Is there also an analog to the fractional effect?
The answer is yes. Has been shown, has been seen. Yeah. And
what kind of fractions are they?
Well, odd fractions. No, I again have to be careful now. What is relevant here, and again this is the big area which I did not discuss, is what the entire picture I've given is by how do you call non-interacting electrons, right? We just have a band structure, and then we start to throw in these electrons, and if we have 10 in them or 100 or 1,000, doesn't really matter. The only thing we say starts to occupy all these levels. It does not start to modify the states, it only occupies that. And clearly the fractional quantum Hall effect is a measure of electron-electron interaction. So the interesting thing about graphene is that this, because of the two-dimensional nature, and also because of the fact that your Fermi velocity is constant, the nature of electron-electron interaction changes compared to semiconductors. So this fractional quantum Hall regime is a very interesting one because it's in a different parameter range. And I cannot really tell you the difference because I'm not an expert there. But certainly it has been observed. Also in suspended graphene. Because then you get the highest quality material.
Yeah, an optical experiment, if it's possible, the graphene diffract the light like a lattice, give a diffraction pattern after with some wavelength. I mean, it's possible, the scale between the size of graphene and the size of the wavelength of the light. Can they interact and they give a diffraction pattern or not?
Okay, you're not talking about super lattice, just about graphene.
No, just one lattice.
No, but I mean, then you have to have wavelengths which are of 1 angstrom, which would be like electron beam. I think there was something question which you could achieve
diffraction then.
By electron diffraction. I'm not sure if this has been done. Probably it has been tried. But I don't know of I don't know any
Because
example.
maybe it's a very easy way to check if it's single layer or double layer. Even more easy than applying these contacts and checking the whole effect.
It's a good remark. But I don't know about if it has been done already. Okay. No more questions. So I hope that I've given you a bit of a flavor of graphene as a very interesting material. Where we are heading, it's not clear in my opinion. Basically, I think the nice thing about graphene is it has something in it for everybody, including high energy physicists and well, practical people like experimentalists. Of course, André Geim will also have a part of the story, but maybe you will approach it from a different point of view. I'm pretty sure that André Geim will do that, knowing André Geim. Thank you for your attention.
Thank you.